All right, guys. The t-shirt that I'm wearing today is very thematic. One of the systems that we really want to take a look at after we started taking a look at the operational amplifier and the voltage transfer characteristics, there's a very common amplifier circuit called the inverting amplifier circuit that we really want to explore. It's one of the simplest types of amplifier circuits, but I can't overestimate how useful it is. So the place where we're actually going to begin is, let me go ahead and let you know what we're actually going to be taking a look at. We're going to take a look at the inverting amplifier circuit. And let me state off right off the bat what the goal is. So the goal is going to be to find what the voltage output is going to be as a function of the voltage input and the rest of the components that are surrounding the circuit. So these are going to be two resistor values. For this one in particular, it's going to be RF and RS. So without kind of further ado, let's actually draw the amplifying circuit, the inverting amplifier circuit. So here we have our operational amplifier with our non-inverting and our inverting terminal. The very first thing that we're going to do is we're actually going to hook it up to the external power supplies, plus and minus VCC. And at the non-inverting input, we're actually going to ground it. At the inverting terminal, we have one resistor here, RS, which is going to be connected to our input voltage source, Vs. Then we have a negative feedback resistor that goes from the inverting input all the way out to the output, like so. And this is RF. And here we have our voltage output, V naught, like this. Right. Now, one of the things that we had discussed previously was that all of the voltages on the operational amplifier terminals, they're node voltages. And one of the things that I found is that the most convenient technique of circuit analysis whenever you're faced with an operational amplifier, because you can use multiple ones, is the node voltage method. So here we're actually going to use the node voltage method in order to analyze the circuit. On top of that, there's a major assumption that we're going to make regarding the nature of the operational amplifier. This is an assumption that in later classes gets modified. We are going to assume that the op amp is ideal. Remember, this actually has two consequences. First is we have the voltage input constraint, as well as the voltage, the current input current constraint. So because this is an ideal op amp, there are two constraints that we can state right off the bat. The first is that the node voltages at the inverting input and the non-inverting input, they're equal. I'm going to use that as an equation 1, and you'll see where we use it here in a second. And the second is the input current constraint. That tells us that the current flowing into the inverting input and the current flowing into the non-inverting input, those are 0 as well. And again, you'll see where we use those here in a second. Now, if we go back to the op amp, let's go ahead and identify the nodes. This is something that we always do in the node voltage method. Notice that there's one node right there. There's another node that circles this entire thing, right? And we'll give these names here in a second. There's another node right there, and then there's one last node right there apart from the ground node. Now that we have the nodes identified, we can give them labels. While this node right here is clearly the P node, the node voltage there is going to be VP, And in general, there's going to be a current that flows from that node into the op amp that is I sub p. This node up here is node N. We can label this node voltage at Vn, and in general, coming from the node into the op amp, we have a current I sub n like this. The node over here is already at a node voltage V sub s, and the node over here is already at a node voltage V sub naught. Now, notice that I still haven't used the input voltage or input current constraints. I'll use those here in a second. Right? But the place where I'm going to start in terms of the analysis, apart from the labels that we have here, is I'm actually going to use KCL at node n, write down a node voltage equation. So KCL at node n, right? And to stay consistent with the convention in the textbook, we're going to say that the sum of all of the currents flowing out of this node add up to 0. Now, there are a total of 3 separate currents flowing out of this node. We have a current going from node n over to this node. We have another current going from this node n, all the way out to the output, and then we have a current flowing from there out into the operational amplifier. So we can write down the currents for each one of those. Make sure the resistor doesn't disappear. Let's go back. So the currents that we have are going to be V sub n minus V sub s, and I'm sorry, that's not V sub s, that is, we called it, oh yeah, we did call it V sub s, okay, divided by R sub s. So here, just to reiterate, that's the current going from there to there. Then we have the current flowing from, oops, bear with me, we'll get this right. So let's put back what we had. See, even instructors have a little bit of technical trouble from time to time. So the current flowing through that node is V sub n minus the output voltage, that's V naught, divided by the feedback resistor, that's R sub f. So that takes care of the second current. And then lastly, we have the current I sub n, right? In later classes, this current itself may take on a value, right? But here, we're going to include it for completeness. So here we have plus I sub n, and that's equal to 0. So this is going to be our equation 3. Now, before we work with this equation and use equation number 2 to simplify it a little bit, I do want to make one observation. And it really has to do with what is the node voltage V sub p. So let's make a quick observation. Now, the node P is connected to it. Right? So if you take a look up here, and I were to highlight this, notice that this node voltage, V sub p, well, it is the ground voltage. It is the 0 voltage. So we can definitely say that V sub p is equal to 0 because it's connected to the ground. And now we can actually use the input voltage constraint. So here, I'll call this 4, and I'm going to use 4 in 1, which means that V sub n, which is also equal to V sub p, well, that's equal to 0, right? I'll call this equation 5. And now I can use equation 5 as well as equation 2 in equation 3. So I'm going to use 5 and 2 in 3. And it simplifies quite a bit, right? So if I rewrite that equation, we have V sub n minus V sub s, order matters, where V sub n minus V sub s over R sub s plus V sub n minus V output over RF plus my sub n is equal to 0. So I just copied equation 3, but that's 0. And so is this. And so is that. All three of those things disappear completely. This also implies that this equation can be cleaned up a little bit and rewritten as v sub s over r sub s minus v sub naught over r sub f. That's equal to 0. I am solving for v naught, so I can add v naught over rf to both sides. So here I'm going to keep that like this. Here I have v naught over rf. If I multiply now both sides by rf, well, these two by construction cancel, and what we're left with is minus rf over rs divided by vs, and that is equal to v naught. Now, it's customary to write the output voltage on the opposite side like this. So that whole equation can be rewritten like this, and this is literally exactly what we were after. Remember, our initial goal was to find the output voltage as a function of the input voltage along with the rest of the components that are there. Now, another quick observation, and this really has to do with why it is that we call this the inverting amplifier circuit. The observation really has to do with the minus sign that is right there. Notice that if I input a positive voltage value, so if I input over here a voltage with this polarity that's positive, then at the output, because of the minus sign, it's going to invert it at the output. We're going to get a negative voltage. If I input a negative voltage, that minus sign that multiplies to give us the output voltage, it will invert it. It will actually turn it into a positive voltage. So this is one of the reasons why this particular circuit has that particular name, the inverting amplifier circuit. On top of that, one thing that I also want to make mention of, so here the observation is that if the input voltage is positive, then the output voltage is negative. So it's a two-part observation. And similarly, if the input voltage is negative, then the output voltage, V naught, is positive. One last thing really has to do with the magnitude of the output voltage. Notice that we can actually control the magnitude of the output voltage by controlling the value of the feedback resistor. If we actually make the value of the feedback resistor, let's say very, very, very large compared to the resistor RS, then we can actually obtain that output voltage to be a very large value. Similarly, and sometimes these are needed as well, if we actually make RF very, very, very small compared to RS, then rather than having a very large output voltage, we can actually turn it into a very small output voltage. But we can control the magnitude of the output voltage by controlling the value of the feedback resistor in comparison to the resistor RS. So one last observation. We can control the magnitude of the output voltage by changing or adjusting the value of the ratio RF over RS, which goes by another name. This is also the voltage gain. We'll talk more about other op amps, but I think it's perfectly okay to leave it here. I think we covered more than I wanted.